You know, we usually think of major programming languages as these pristine things, handed down from an ivory tower, right? Born out of pure mathematical theory. But that's absolutely not the case with C++. In this explainer, we're digging into its incredibly scrappy origins. It's a story driven by raw, frustrating necessity. We're going to see how Bjarne Stroustrup built one of the most influential tools in history, not by chasing academic perfection, but by obsessing over what programmers actually needed to just get their work done.
Just think about the sheer audacity of his initial goal here. Stroustrup wanted the beautiful, elegant program organization of a language like Simula, but he wanted it mashed up with the blazing efficiency and total flexibility of C. Oh, and get this, he wanted to deliver it to real projects within half a year. Stroustrup himself later admitted this was a completely preposterous timeline with draconian demands, but against all odds, he actually pulled it off.
So, here's our roadmap for this 12-year evolution. We'll hit the quest for better tools, the birth of C with classes, its evolution into C++, the addition of powerful new language features, and finally, Release 2.0 and standardizing the whole shebang.
Starting off with Part 1, the quest for better tools. Let's set the scene. It's 1979, and Bjarne Stroustrup is working on his PhD at Cambridge University.
He's trying to build this incredibly complex simulator for a distributed system, and he is just slamming headfirst into wall. On one hand, he had Simula, great language, beautiful organization, ideal class concepts. But the runtime overhead, absolutely brutal. We're talking 80% of his program's time being eaten up by the garbage collector, even when its simulator wasn't actually producing any garbage. He couldn't afford that, which forced him to rewrite the whole thing in BCPL. Now, BCPL was blazing fast, basically matching C, but it was a nightmare to write in. Zero static type checking. It was just a rigid, frustrating straitjacking.
Swearing he'd never suffer through tools like that again, Stroustrup laid down some extremely strict ground rules for a new language. It absolutely had to have Simula's high-level design support, classes, concurrency, all that good stuff. But it also needed the fast execution of C, simple linkage to combine code easily, and it had to be highly portable without dragging along some massive, complicated runtime system. Essentially, he wanted high-level architecture combined with extreme, down-to-the-metal performance. That brings us to Part 2, the birth of C with classes. This quest led him straight to Bell Labs, where his very first major challenge was analyzing network traffic for a Unix kernel distribution. Now you have to understand, the stakes for performance at Bell Labs were sky high. At one point, a colleague showed that this new tool caused a systematic decrease in runtime efficiency of just 3% compared to plain old C. Just 3%. But at Bell Labs, that tiny overhead was instantly deemed completely unacceptable. Stroustrup had to rip it out immediately. C with classes had to match C flawlessly in runtime, code size, and data compactness. Zero exceptions allowed.
A question that comes up a lot is, why C? Why not Pascal or something else? Well, he chose C because it's flexible, insanely efficient, and practically everywhere. He wanted to stay firmly in the mainstream of systems programming. More importantly, he actively wanted to avoid this sort of misguided paternalism you see in other languages, the ones that try to force you into a single stylistic straitjacket. C gave him that perfect, unrestricted foundation. Moving on to Part 3, the evolution into C++. Fast forward to 1982. C with classes is what Stroustrup called a medium success. It paid the bills, sure, but it wasn't quite hitting the mark. So, he teamed up with brilliant colleagues like Doug McElroy, using a collaborative Blackboard design approach to build something way more ambitious.
To achieve that extreme portability he was chasing, Stroustrup didn't just build a standard compiler backend. Instead, he engineered this absolutely brilliant workaround for the very first C++ compiler, which was called CFront. The whole pipeline begins right here, simply with your raw C++ source text. That raw text was first fed straight through the standard C preprocessor, or CPP, just to handle all your basic file inclusions and macros.
From there, the output went into CFront itself. This was the actual C++ compiler front end. It did all the heavy lifting, complete syntax and semantic checking of the code. This is a super important detail because it completely debunks this old myth that CFront was just a glorified macro preprocessor. It wasn't. It was doing the complex work of a real compiler. But here is the real stroke of genius. Instead of spitting out machine code, Stroustrup brilliantly generated standard C code. That generated C code basically acted as a highly portable assembler
Because C compilers existed on pretty much every machine on the planet, Stroustrup could just feed this output right into any system's standard C compiler.
And finally, that standard C compiler produced the executable object code. This clever pipeline was the ultimate existence proof. It proved C++ could be incredibly effective literally anywhere C could run, whether you were on a massive mainframe or an early personal computer.
Which leads us to part 4, powerful new language features. As the language evolved and officially got the name C++, some really complex features were added. But the key takeaway here is they were never added just as theoretical experiments. They were added strictly to solve gritty, real-world problems for working programmers.
Take his famous 1986 paper titled What Is? Here, Stroustrup clearly defined object-oriented programming for the C++ world. He described it as expressing the distinction between general properties, like the generic concept of a shape, and specific properties, like a circle. By using inheritance and virtual functions, C++ let developers extend software systems safely without having to constantly rip up and rewrite the existing core code. A real game changer.
To make all this work, a whole suite of powerful features got bolted on. Virtual functions were pulled directly from Simula. Operator overloading was added, which made complex math and matrix operations so much cleaner to write. He brought in references to pass massive objects efficiently without messing with raw pointers, added the const keyword to protect data, and introduced new and delete for precise memory management. Now, were these controversial? Absolutely. Features like operator overloading sparked massive internal debates about compiler complexity. But Stroustrup pushed them through for one fundamental reason. They empowered the programmer to write cleaner, faster code.
All right, part 5, Release 2.0 and standardization. By the late 80s, C++ was exploding. It had moved way past being a one-man research project at Bell Labs and was rapidly morphing into a major commercial reality. But of course, commercial success brought the grueling compatibility wars. Management and new users were demanding 100% compatibility with older C dialects. Stroustrup fought exhausting, brutal battles over this. His mantra was steadfast: C++ as close to C as possible, but no closer. He totally recognized the need to be highly compatible to drive adoption, but he flat-out refused to inherit C's dangerous loopholes, like implicit type violations that just cause silent catastrophic bugs in production. So he tightened up the type system to actually protect the programmer.
This relentless pragmatism kicked off a massive decade of growth. From that scrappy internal tool called C with classes in 1979 to getting the C++ name in '83, the milestone Release 1.0 in 1985, all the way to Release 2.0 in 1989. By that point, C++ wasn't just an experiment. It was a major commercial powerhouse featuring advanced concepts like multiple inheritance, and it was being used by thousands of developers all over the world.
So that leaves us with a really fascinating question to ponder. Is the ultimate goal of software engineering to achieve pristine academic perfection, or is it about trusting the individual programmer, giving them pragmatic, sometimes messy tools, and letting them shape our digital reality? Bjarne Stroustrup's journey with C++ definitely proves that when you prioritize solving real problems over chasing theoretical purity, you can build something that quite literally changes the world. Thanks for joining me on this explainer, and keep exploring.